Hello. Hi everyone. How are you doing? How are you doing today? Glad to greet you all. And today I'm doing another small talk, mini talk about type classes. I hope the sound is okay and the picture is showing. And if everything is fine, I can start talking about that. As usual, you can ask questions in the chat. I see it. And yes, I hope we will have some insightful evening today. It will be a small talk, I mean a little talk, because it needed some time to prepare. I prepared something at least, but never mind. So, type classes are not interfaces. Why? And why actually we want them in our languages? Uh, do are we um, are, don't we have other tools to solve the same tasks? Why type classes and why they are not a good analog of OOP interfaces, or saying widely why they are not a good representation of the concept of interface, of the idea of interface like abstraction. Well, first of all, in Haskell we use type classes very much extensively, and we use them for different reasons, different purposes. And some of those reasons indeed include using type classes as interface like abstraction, and this makes code bases a little bit more complicated compared to the case if we used true interface like abstractions instead of type classes. I'll try to show that. So let me talk about abstractions again, like in the previous talk uh, several days ago. So we have abstractions. We have many abstractions, and those abstractions can be divided. Sorry. Yeah, I'm not prepared yet. Those abstractions can be divided into groups: genericity like abstractions and interface like abstractions. And these two groups have very different properties and usage. I see several comments in the chat. Sorry. Concurrent viewers 2. It was 7 of them when I started and 2 right now. People decided to leave immediately when I started talking. Alright, Arseny Alfeev says Rust traits equals Haskell type classes and question mark. That's an interesting question, because yes and no, and I would say no rather than yes, because traits in Rust have a very they have many facets. They can serve as Haskell abstractions like Haskell type classes. They can be type level genericity mechanism to provide some properties for other types. But actually they are used as OOP interface like abstractions, and I believe, I'm not quite sure, but I believe this usage is more widespread. Maybe maybe this usage is more widespread in regular development, but using them as type classes or genericity like abstractions can be seen in library development. And this separation is not a coincidence, because genericity like abstractions like concepts in C++, which are type classes essentially, generics, templates in C++, again it's like generics but not quite, but we can consider them generics. Those things are very usable in library development, abstract libraries for something, for data transformation, mm, for algorithms, for data structures. Genericity-like abstractions work great in that setting. But when we are trying to use those abstractions for mm, business and setting, like abstracting some business notions and ideas, the code starts being too coupled, because in general the abstractions to the left of this table, genericity like abstractions, they work on the level of types, and mostly they disappear when the program compiles, and they don't have an idea to hide information. They do not hide information, they generalize information. It's like math equations. You can expand math equations if they were um, shortened at some moment. It doesn't, for example, you have a math equation that looks short, but you know that for a specific symbol there is a whole world of underlying notions, and they are not just hidden, they are there in that symbol. You can substitute that symbol by those notions, and a big chunk of equation, big chunk of a different equation becomes a part of your beginning equation. So the genericity like abstractions are like this. They are expressions. They do not hide something, but interface like abstractions hide information. They have this property, information hiding, and they encapsulate some hidden info, maybe implementation details behind the interface. They encapsulate these implementation details in implementations, and this is a very drastic difference between the two. Because interface like abstractions, their purpose is not to generalize, their purpose is to reduce complexity. They are not expressions, they work at runtime. They, well, we can't really say they disappear at runtime, but they work at runtime, and objects or implementations that we have behind some interface, they have a lifetime. They can be seen as separate entities somewhere in your memory, and they act in runtime. So interface like abstractions, they unify and hide implementation details. Genericity like abstractions doesn't have this idea behind. They do not hide something. So you can see the comparison between the two. Genericity like abstractions can be used for identifying different idioms, like on the previous example, previous slide. Those idioms like foldable, traversable, common-add, one-thread, etc., etc., etc. Haskell has millions of those abstractions, and they can be applied to your types. So genericity like abstractions can be applied to types, but interface like abstractions can be applied to notions, and this is very important. Let's take a closer look at interface like abstractions. For example, interface keyword from Java, the feature interface, and I would say that OOP and interfaces have a distant relation to each other. The notion of interface, the concept of interface, is not an exclusive property of OOP. You don't need to, there is no real belonging of interface as a concept to OOP, because interfaces are everywhere. USB is an interface, and it's called an interface not by chance. it's an interface because there are many various USBs, and you can be sure that if you plug in this USB into the same USB slot, your device will most likely work, because that's the idea of interface. It unifies something. There are interfaces in various branches of engineering. For example, in airplane construction, there are interfaces, so you can replace some devices because they have the same protocols and even the same slots to be plugged in. So interface is a more general notion than just some feature from OOP. In this regard, we might heard that, oh, they are trying to make Haskell Java by bringing interfaces into that. That's an invalid statement, because we don't make Haskell Java, we make Haskell engineering, because interfaces is where a true engineering starts. Interfaces help to reduce complexity in some way, and it's just a little of coincidence that Java and C# used this keyword for their feature. So you can see two simple interfaces here, iLetter and iEnvelope. And take a notice that iLetter has a method translate. We could say this method is pure in our pure functional language, but in Java we don't really know. Maybe it mutates and changes the internals of the object behind. This possible. In Java we cannot tell the difference, but it's not the main point of this method. This method returns iLetter, another instance of iLetter, and this is what interfaces in Java can do, and this is what type classes in Haskell generally speaking cannot do, but they can using some additional type level magic. This will be the first and probably the main difference, but not only. So it's a simple example, right? iLetter, there is an envelope that returns iLetter, and iLetter can return iLetter itself translated to another language. So it's a very simple, two very simple interfaces, and implementations are also simple. For example, we have a simple letter and a gift card that can be like a letter. There is a basic envelope and there is a secure envelope, whatever this means. Maybe it's a digital letter envelope and you need to type some code to open the envelope. Well, in Haskell we probably can declare type classes for that, and take a look at this syntax, right? Get content, we should provide a letter and we'll get a content. Translate, we should provide a letter, a language, and we will get another instance of iLetter. This looks quite okay, but when we try to do several interfaces interacting to each other, it turns out that we need to specify more type arguments in order to support this hierarchy, and this thing works on the level of types. It's no longer nested one into another. Those two interfaces, better say type classes, are kind of they hierarchical, but hierarchical on a different level of language features. They're hierarchical as type expressions, not as notions nested into each other. Yes, you can design this code differently for sure, and there is no need to have type classes even. It can be done differently, but I want to demonstrate the difference, right? I want to demonstrate why type classes lack several properties. So when you have such an expression with some constraint here, this expression will go into your business logic functions, and you will have to support that. And this is not a very convenient design, because the more interfaces you have in your program, the more you will have constraints, and those constraints will pollute every possible function, because interfaces need to interact somehow. But in Java or in C++, those interfaces won't be expanding like crazy. If you need to pass some envelope, it will be only an envelope and nothing more. It will contain iLetter, but the variable will be only one, without extra complexity. You can have dozens and dozens interfaces here internally. It doesn't even matter that those interfaces are used as return types. They can be types of variables. It doesn't matter, because the only thing you need to know is envelope, and the code is easier to write. But once you have type classes, you still need to put those type constraints in many places, because you still need to use this type class inside some function, and you have to provide some evidence that there is type class for this L. So and this is only one nested interface, right? Imagine how much complexity there will be if you start adding more interfaces. This is, by the way, started looking like if you add more interfaces, well, type classes, you will get some MTL style, or maybe final tagless style in Haskell. And my point is that final tagless and MTL are extremely boilerplatey things when you need to write business logic. Alright, so this is not the only limitation, actually. There are several more. Now, let's say that we have several implementations for iLetter. Simple letter and gift card, right? And two implementations for envelope, basic envelope and secured envelope. And this is a Haskell code, right? In Haskell, you have to provide some instance for each, or maybe instance for separate iLetter and envelope, but you have to make them put them close to either the types or the type classes to avoid orphan instances. This is another limitation, because well, you can avoid, you can proceed with orphan instances on your risk, and Haskell will only bring you warnings. But a good practice is to avoid orphan instances. I don't quite agree with this practice, because in practice, in reality, in real programs and real projects, you don't often have access to basic envelope, I mean implementations, to envelope, I mean interfaces. They can be defined in several places you don't control. For example, separate libraries and foreign projects. You still have to provide some instances for that. I don't even say that the number of instances grows as you add more interfaces, but you have to provide some instances, and you will have orphan instances for that. This is another limitation. In Java or in C++, in other OOP languages, there is no such thing as orphan instance. It's a very idea is the very idea of an interface. It can be defined in any place. The implementation can be defined in any place. If you need to merge them, you can create your own instance of that. So there will be no extra complexity in that. And yeah, this requirement comes from the type checker, because it needs to know it needs to resolve your type classes and constraints, and when it has several of them competing implemented for the same thing, it gets lost because it doesn't know what to do. So there is a requirement of not be orphans in your projects. Another limitation comes when you try to put your interfaces, I mean in objects and notions, into a collection. With true interface-like abstractions, it should be an easy task, because this is a very widespread business scenario. You need to have various implementations of some subsystem, or maybe of some business notion, generic business notion that should have various implementations, and you need to substitute them on the fly. And you do that by storing your objects into generic collections. And in OOP languages, this is as easy as it can be. In Haskell, you cannot do this easily, because again, type classes they work on the mixed level, type level plus value level, and mostly they work on the value level, on the type level. And to put them to the value level, you need to either existentify them or valuefy them, because type classes typically get erased when the program is compiled, and they disappear, contrary to interfaces. So there are at least two ways to put your instances into some collection. It's existentification and valuification. In both cases, you will lose some information that is tied to the type class, and you will have some limitations on what you can do with those objects behind the type class. Let me demonstrate you some existential wrapper for a letter. It's an algebraic data type. It's not a simple algebraic data type, because it contains a type class internally in one of their value constructors. This type class says that you can store any L inside this LV, and the information about this type class and L will be only available when you pattern match over this LV. It will be only available in the subsequent code, or when you pattern match over that, and it cannot leak from here. It cannot escape from this value constructor to the upper code. So when you do this wrapping, it's mostly you enclose this information inside, and you cannot access it otherwise than pattern match and use it in subsequent calls. This is often a problem, and in real programs you need to return, for example, some of those values and do something with them. You certainly can do this with existential wrappers by having more specific methods that work with those instances inside of the wrapper. Well, now you can put your instances, for example, simple letter and gift card, into a list, and this will work. You then, when you pattern match over LV, the methods specified for iLetter will be available for those two instances. But once you have more type classes, things are getting crazy, because you need to provide those type classes again, type constraints. And for L, you don't have L here, it's envelope. There is some letter probably inside of this envelope, but there is no letter here. You only have an envelope. So one of the solutions to provide this constraint is to put a proxy that says there is no value of L, but I will be a representation of that L for you. And yes, we got some extra complexity without any real need in that thing. Imagine what will be if you have even more interfaces. This all should be carefully prepared, and I even have some problems in defining such an existential wrapper, and yes, it won't be an easy task. So this is the main limitations of interface in general, of type class. In general, type class has three limitations. It cannot return values of type classes, generally speaking. It doesn't do encapsulation, it doesn't do interface, it doesn't do information hiding. So, and reducing complexity is not the main task of type class. And this is a true interface. You know, it's a free monad, and this free monad abstracts to internal algebras, to internal representations of letter and envelope. So letter and envelope are free monads. Use it as interfaces for some objects, and there is no problem in those methods returning another free monadic interfaces. There is no extra complexity here. There are no extra type parameters here for that. You just use the interfaces, free monadic interfaces, as you would do it with Java interfaces and OOP interfaces in general. But those are not in OOP interfaces. They might look like so, but they work completely functional. They are functional, and this is the best counterpart to OOP interfaces in functional world, because they have many various interesting properties. Being monadic means being very convenient in some scenarios, and also they do not have those limitations as type classes have. And as you can see, we can just put those things into our collections and everything will be fine. So type classes are not true interfaces, while free monads and interpretable languages in general are true interface-like abstractions. So as I said, genericity-like abstractions often used in abstract libraries, and this is where the confidence in type classes comes from. Haskellers are accustomed to type classes, and they think this is a very great abstraction, but it's not, because it's a leaky abstraction. Once you declare some type class, you cannot hide what it expresses. You will have all those implementation details leaking into your client code. It makes the code even very highly coupled. So type classes do not solve the problem of high coupling. They increase coupling actually. And also, if you use some external libraries with those type classes, you will immediately notice that your code will hugely depend on the internals of those libraries. For example, some generic collections, they provide own type classes, and you put those type classes into your code, but in some point of time you can decide to replace some generic collection by another one, and suddenly type classes may change because different collections provide different type classes, and you will have to change a lot of code. I say nothing about foldable, traversable. These idioms very universal, and yes, many generic collections implement those type classes, but also generic collections provide own type classes for something, and this is an implementation detail actually. It's like if our collections in Java could provide how they are built and what they do inside internally, and the client code should rely on that information for some reason. But in our applications we mostly need interface like abstractions to express business entities and put them into collections, to express subsystems. Haskellers love calling it effects. Also, plugins cannot work without interfaces, and interchangeable implementations that you can substitute on the fly, cannot work with type classes, because type class instances are are once defined, cannot be changed. They are properties of types, not implementations of interfaces. So if you use type classes for that, you can see that the complexity increases in your applications, and I generally don't recommend that. Here you can put your recording on pause and take a look at what a true interface like abstraction should be, what properties it should have. I won't be reading that. But limitations, right? Functions should have type constraints, which is very inconvenient. This practice is only seen good in languages like Haskell and maybe in Scala a little bit, but in the rest of the world this doesn't look a good practice. Type classes cannot return other type classes as interfaces, or they can with hacks and increased complexity. You also need existentification and validification for putting instances into storages and collections. Implementation details leak through the type class. There is no separation of runtimes and environments. When you do interfaces, let me open some interface. When you do interfaces, the internals of the implementation, like here, is an environment in which this implementation performs its activities, and this environment is completely separated from the external code. You can get those implementations from external library, for example, and they will do something internally. You don't even need to know what they do, and this environment will not affect your environment. With type classes, it's not the story. Once you have this constraint, it means it will be a constraint of your business logic. It will be your environment of your business logic. So you cannot separate them. There is implementation, instance of each, but this instance will only work in the environment you provide and in your business logic environment. So they don't have separate lifetimes. They don't have lifetimes at all, to be honest. But if you use free monad, those objects behind the interface can have own environment, but not in like in OOP. There is actually no implementation detail behind every notion. Not here, not here. Those notions are not containers for your implementation details. Those notions are descriptions of how to convert your implementation details. And implementation details will be specified with interpreters. Interpreters of free monads can have lifetimes. They can have own separated runtimes and environments, and those separated environments will not be interfering with the main environments of your business logic. So those are completely separated, as they should be. That's a very important feature of a type class, of a free monad, and of any sane interface like abstraction. No lifetime control, no complexity elimination, no information hiding, cannot abstract objects. Yeah, free monads can abstract both objects like here and also behaviors. And you can do very impressive things with those interface like abstractions. So that's probably it, and I hope it was clear. Maybe I even forgot several interesting moments about type classes, but in general they're very bad as interface like abstractions. Thank you. Yeah, that's it for now. Well, I have some extra content. I have different languages, and can show you how type classes work in different languages. For example, in C++. In C++, there is a notion of concept. Concepts are actually type classes with some specific subtle differences. Those differences are certainly important, but they are not as much as important. You can use those concepts as type classes in C++, more or less. Well, we can also say that templates are not generics. Still, they are very, very similar to generics in how we use them. So in C++, we define a concept Fight Club rule. And this rule should have only one method, explain. This method returns a string. C++ has a very strange syntax, yes. Then you can define several rules of this Fight Club, and those types will be independent. You can have them separated into different projects, and they don't need to be in one place. This is very good because in general you want to have implementations from different sources, right? And then we need to create an existential wrapper, because we cannot put those rules into a collection. They don't have anything in common except only one thing: they all have the explain method. In C++, there is no duck typing like in Python or other dynamic languages, and we cannot put those structures as is into the same structure, into the same collection. So we have to specify some wrapper. I see several comments. When we should use type classes or interfaces in languages supporting both AG Scala as Apollo. You can take this slide as a rule of thumb. Let me show. The classes, compile type polymorphism. Yeah, you can take this slide as a rule of thumb. If you need some generic algorithm that will work for some unknown structures and data types upfront, not for behaviors, not for objects, not for runtime working entities, but for some types that can be defined on the level of types, then you certainly need type classes. If you need to specify some behavior or abstract some notion that has a runtime representation, you need to use interfaces. This is the general rule, but certainly there are many exclusions from this rule. So in C++, we can define another existential. This existential will ensure that we pass something that has this concept implemented for it, and we cannot just put it as we did in Haskell. We need to stringify, or sorry, valuefy the rule, and we have existential plus valuified wrapper here, and valuification means we put the object and its behavior into a lambda and erase the information about the object. There was a rule object, it had some Fight Club rule, we put it into a lambda, and the only place we access the type class, the concept, is inside this lambda. It's not visible from other places. In other places you only have a lambda that returns string. This is how you can remove the information about type class, effectively existentify it and valuify it, and after that you can put all those things into a collection with secrecy wrapper. In Rust it's the same story. There is a trait, this time used as a type class, and it has an explain method, and implementations of this kind of type class also can do things, and they are independent, and putting into a wrapper means passing this. Well, this is a very strange syntax too, very strange to me, but there was an error as a type, and it was a static type and the object, and we need to convert it to a dynamic value here, and forget about some internal properties. We only know it was Fight Club. In this case, we do not erase the information about the type class, well, trait, well, interface, and the box will contain a dynamic representation of that, and can use dynamic dispatch as it was an interface. So this is our existential wrapper, kind of, and then we can put all those things into a collection. So you can see the the idea quite the same. The idea quite the same, and can be applied in different languages. There is a Scala version of that with traits. It uses implicits. I don't quite understand this code, but you can do that. Also, you need a wrapper. In Scala, it's better to use OOP because you don't have to do wrapping, right? And you can use trait as an interface and effectively remove all that complexity, and just put your objects into into collection without implicits. This one is OP inheritance of an interface. So Scala states can work this or that way. They're mostly the same, except this is a parameterized one and this is not, and this one uses implicits to convert something to something, and this one doesn't use implicits. So this is where a dual nature of traits can be seen. That's it, probably. So maybe you have some questions. If not, if you don't have questions, then we can finish at this moment, or you can ask questions and I can talk a little bit more. All right, I see some comment. Let me hard to see it. Polariso writes, it sounds like free is the best solution for interfaces in Haskell then, which means you're always using an interpreter to evaluate the interfaces to some implementation. Is there other solutions? Other solutions? My answer, yes, but I'm very opinionated. Yes, I do think that free monads in Haskell are best for interface-like abstractions. Where is my slide? Where is my slide of that? Yeah. Other solutions can be, for example, service handle pattern. It is a structure that contains various lambdas inside. Those lambdas like methods, and they do something. They hide some implementations behind. This service handle pattern can be seen as a interface-like abstraction similar to interface in Java, and can be used like that. Maybe not a bad option, except it doesn't contain mutable objects behind. Well, it can. We can bend it like so. I mean, if you have a service handle pattern, several methods, then you need to provide some additional fields for that mutable object behind. Otherwise, you will only have some. Well, actually, you can encapsulate mutable variables into those lambdas. Yeah, you can actually. Yes, I think you can. Some thoughts. So how to explain? Well, maybe we can just open a code and I can show you data. For example, iLetter. iLetter. Oh, it's another language. Sorry. iLetter. iLetter. For example, iLetter. What we had, translate something to iLetter, and also we had a method. What did we have? Get content. All right, get content. Get content string. This will be our service handle pattern. So service handle, right? It's a handle, and we can define simple letter, for example. my content string. And now also we need something else, right? Simple letter, gift card, image, for example, image white string, just a picture in some format, string, like that. And we need a generic, not generic, but a common function that works with iLetter and doesn't know about those two implementations. For example, print letter, iLetter, IO. Now, what we can do? We only can translate and get content, right? Translate is not interesting to us in this function, but we can get content. Let content get content L, and we should print it. Print content. This function doesn't know about implementation details and should not know. It's our business logic. Now we need to call this function for different implementations, right? Print letter, and here we need to define that interface, mk letter, from simple letter but ABC. And this mk letter, well, yeah, it's a helper function. It should work for both of them. We can separate them. mk letter from simple, or we can use a type class for that. Well, let's do it easily. Simple letter, iLetter, simple letter, and we have content. And now we need to fill our handle. It has two options: translate and get content. iLetter, translate. Well, we also have a language, right? Translate to some language. Data language. Let it be empty. Or maybe translate. In this moment we need to put a lambda here. Lambda something, language, translate, language, content. I hide the information about the actual simple letter behind lambdas. This is a verification. The idea is the same. Get content, get lambda, get content, just returns content, right? Just content. Byte string is not available. Let's call it string for no reason. Could not much expected. 31. Language, translate language. I did something wrong, right? It should return, alright, it should return another iLetter. It should return another iLetter. translate. We need to call a specific translate function. There should be a specific implementation of that function. Well, let's just say it's kente, and this will be another simple letter, and this will be another call, I guess. Yeah, exactly. So I wrapped my simple letter into iLetter. The more functions I have here, the more methods in this interface, the more wrapping I need to do. And if I want to have some mutable data, one of options can be, for example, we can import IRF, and either can put this option IRF here, my variable content, for example, IRF string, it will be a content, or we can enclose the same variable in here. Suppose we have a mutable simple letter. It's not just an immutable content, but maybe something that we can change. The things are getting more complicated. New IRF ABC, and now content ref. So those functions should be IO now. They cannot work with pure content, and this is a typical service handle pattern. Most of them are impure, and most of methods are impure, and I can do this like here, IO letter, and also we need to make a letter first. Oh, sorry, because we will do some readings and writings here, and only then can return something. It's not longer kente, but ref. Kente read IORef. Now we can translate. Let translated. In Haskell, it's a lazy evaluation, so it will not be done unless it's needed. At least we can hope for that. Now we need to create another IORF, right? Because it will be another instance of iLetter. Simple letter. Oh, sorry, translated. New content, or better say, related ref. Let new simple letter translated ref. And iLetter should get language and should return iLetter, right? Translate to lang is not known here, so we need to pass it. Translated lang, translated ref. It's difficult to understand what I should do. there will be a function that calls length, so we need to have let translated wrapper probably. Translated and like that, right? Pure translated wrapper. It will return simple letter, but it should return I letter. We can put it here. And pure new letter. Maybe it's like that. And we enclose it. We capture the IRF inside some lambda. You don't see lambda here, right? But it will be there. Translated wrapper and some content. Content can be just pure content. Maybe like that. Print letter. Letter printing also will be in pure. With content will be IO string. Maybe I'm mistaken. Maybe I put print content. Maybe I did some mistake. 42 pure. That works, actually works. So now it's a service handle pattern, another option for interface-like abstractions in Haskell. That's it. Well, I think we can finish, right? Interesting, thanks, says Polarici. Yeah, you're welcome. So that's it for now, and thank you for your attention, and see you next time. Bye.